Okay, so hello everyone, and welcome to the week number 5 tutorial. And the topic of this week is going to be the planar kinetics of the rigid body. So basically, we're going to complete what we've done last week, but the last time we didn't have the angular motion. Today, we're going to have the angular motion to be involved in the analysis. So we start with this example about the 15 kilogram rod is pinned at its end at A and has an angular velocity omega of 5 radian per second when it's going to be in a horizontal position shown. So definitely this will be left, and then we're going to have an angular acceleration and the pin reaction at this instant. So basically, we're going to analyze this shape now. We're going to have two reactions at the point A. One of them is going to be the vertical. The other one is going to be the horizontal. Okay, now that's what we are going to find. I'm sorry, this one is doing the other way. Okay, so we're going to have two forces. I just put the arrow randomly. And also we're going to have a weight that's working at the point G, which is going to be at the middle. Now we have the omega known, and we don't know what the alpha is. And this alpha can be this direction downward on the clockwise direction or counterclockwise. We have to check that together. So that's what we need to find, the angular acceleration and the pin reaction at this instant, the AY and the AX. So we're going to work on that together, and we try to find a solution. So we go to the next step. Okay, so we give you just a general solution. What we need to do is the sigma of the moment around the point A was going to be, of course, equal to the I multiplied by the alpha, where the I is the MMI, the mass moment of the inertia, multiplied by the alpha. From there, we are going to be able to find the alpha in radian per second. In addition, do the sigma of the forces to the x-axis in the 3-by diagram and take that to the kinetic diagram, and we should have that to be given because that will be the mass multiplied by the acceleration of the point G in the x direction. And we can find the value for the A. Now we're going to get the results from the alpha we had already and do the sigma of the forces to the y-axis, and this will be equal to the mass multiplied by the AGY. Now here, of course, we're going to have the direction AY and the weight was going downward, and we're going to be able to find what will be the AY direction. Remember that on this spot, and this acceleration can be easily found by knowing that the A tangential and A normal, as we did last time, for a bar that's going to be rotating with alpha and omega. Okay, so here we're going to have the two accelerations. That will be the AT, which is going to be equal to the AY, and we have the A normal, which is going to be the AX. So that's what we're going to do to find the solution. So once again, we're going to start with building the 3-by diagram and the kinetic diagram. So you can see here that I just put the links, and I know that the center of gravity is in the middle. Then I'm going to start to put my arrows. So at the point A, I'm going to have the two reaction, AX and the AY. And here at the point G, I'm going to have the weight going downward. So that's what we have in the case of the 3-by diagram. Now let's go to the kinetic diagram. We all either going to have the moment A, G, Y going upward or downward. I don't know what direction is going to be till now. And the moment multiplied, the mass multiplied by the acceleration of the point G to the X is going to go to that direction, which is going to be opposite to the reaction we have at the AX. So again, the alpha can go either clockwise or counterclockwise. I don't know now. I need to calculate if it's going to be positive or negative. So that's what we're going to have. So the AX, that's what we have, and the X direction is going to be equal to the MAX, MAGX. The AY minus the W is going to be equal to the MAGY. Okay, and the moment around the point A is going to be equal to the mass multiplied by that distance. Okay, that's what we have in the kinetic 3-by diagram. And here is going to be this force multiplied by the same distance, the MAGY multiplied by the same distance. So that's mean that the AGY at the end is going to be equal to W multiplied by the mass, and this will be something like 9.8. We're going to check that together. Okay, so now we know the, actually I can, yeah, we need to find the alpha at the end. Now the free body and the kinetic diagrams of the bar has been drawn first, and then we're going to go to the step of doing the analysis. First, we need to know what we have. So we know that the mass is 15 kilograms and the omega is minus 5 radian per second, minus because it's going to the clockwise direction. Now the unknown are going to be the AX, the AY, and the alpha. So we go to the equation we're going to choose here, which is going to be the AX. Sigma of the AX is going to be equal to the mass multiplied by the AGX, that's 1. The AY is going to be equal to the mass multiplied by the AGY, that's 2. We have the moment around the point G equal to the IG alpha, that's one option. And the other option we have is that the MG is going to be equal to, sorry, that's one of them should be MA. Okay, so it doesn't matter. RG to A mass multiplied by G. Okay, so that will be the MA, not the MG. Okay, I need to change that in the slide I'm going to give you in the class. Or actually, I can do it right now while we're recording. So that's the slide we have. Okay, I'm going to change this one. It's going to be up here directly. Just give me 1 second. Okay, sorry for the typo. Things usually happening by mistake. Okay. Okay, and save that. Okay, now we're going to go back home page and come back to here. And now this has been changed to the MA. Okay, so the moment around the point A is going to be equal to the IG MMI, of course, multiplied by alpha, plus the mass multiplied by the AGY multiplied by distance from the G to A. So these are the three equations we're going to use. We're going to check each of them and see how they're going to work. Solution is start with the easiest point. The AGX is unknown. AGY can be found because it's going to be the tangent acceleration. So anyway, I can start to do the calculation. The AGX is going to be equal to the normal acceleration, which is going to be the negative omega square multiplied by the R G to A, and this will be equal to negative 37.5 meter per second. So once again, that's the normal moment we're going to have for rotating bar. Okay. Now, we're going to assume that the alpha is going to be positive, so the AGY is going to be equal to the AGT, and this should be positive. So once again, you remember that the equation we're going to have for the acceleration in the y direction is going to be the tangential force, and this will be the one that's related to the alpha. So alpha multiplied by the distance from the G to the A. So we're going to have that the value of the AGY is equal to the tangential acceleration we have at the point G, which is going to be equal to the alpha multiplied by the RG slash A. And thus we're going to have 1.5 alpha as the answer for the acceleration. Now, okay, further, we're going to continue do the solution with having these accelerations. We have this information. The mass is known as 15 kilograms. And now we start to do calculation for the acceleration. So now, definitely, I cannot start with this one because I don't know what the alpha is. Okay, so the AGY is 1.5 alpha, but I can find now the some a relation between the acceleration, sorry, the AY, the force at the point A to the direction of Y, and the alpha. And from the first equation, I can find directly because I know what the mass is, and I know what the acceleration to the x direction is. So we can start now from the first one, and we can see that by using the x direction equation. The ax is unknown, the mass is known, the agx is known, so I can find that the ax is going to be equal to 15 multiplied by negative 37.5, and this will be equal to negative 562.5 in Newton. And that will tell me that the direction of this arrow is going to be to the left. Okay, so it's try to pull the road while it starts to rotate. Okay, so that was the easy step. We are lucky to have this one. And now we're going to solve for the other parameters, going to be the AY and the alpha. We need to find the alpha. So we have two unknowns, we have two equations, and we're going to work on that. The first equation is find the relation between both. So we're going to have that the forces to the y direction on the bar is going to be equal to the mass multiplied by the AGY. So well, in that case, we are going to have the W, which is negative 15 multiplied by 9.81. That's the W plus the AY, which is unknown. It's going to be equal to the mass, which is 15 multiplied by 1.5 alpha, which is the acceleration GY. So we can write down this equation, and then we're going to solve this equation to find that the relation will tell me the what will be the A in terms of alpha. So next I need to find the alpha, and then again to find the value for the AY. So we start with the moment equation. So the first equation I said is going to be that the moment around the point G is going to be equal to the MMI or about the point G multiplied by the alpha. The MMI, as you remember, is going to be the mass of the road multiplied by its length squared divided by 12. We did that last week. Okay, and thus if I get to add this information in, I'll get this equation. Actually, once again, it's going to have the AY and the alpha is unknown. So anyway, I'm going to reach that stage number, the equation number 3. I don't know if I get to actually going to apply that in the other equation. No, it will tell me that negative 7.5 alpha is equal to 22. Well, actually, I think I can do that. But anyway, I think this will be another relation. We're going to have two relations of the AYs in the terms of the alpha. So I'm going to ignore this one. I will go to the moment around the point A. So I can calculate the acceleration, the force, sorry, reaction at the point A, and I'm going to focus on finding the alpha. So let's go to the other equation, the equation C prime. Now let's look about what we can find here. The moment around the A in the free body diagram is going to be equal to W multiplied by the distance. Okay, here we found that unknown. The mass is known. The AGY is 1.5 alpha, and the RG slash the A is 1.5 meters. So here we're going to have number, which can be found. Number terms of alpha and number terms of alpha, then I can solve for the alpha value. So let's see how we can do that. That's what we have in the free body diagram. This is the MMI multiplied by the alpha. That's the first part. Second part is going to be the mass multiplied by the AGY multiplied by the RGA. So we said that here. We're going to divide that. The weight is minus 15 multiplied by 9.81 multiplied by 1.5. And on the other side, we're going to have the mass, which is 15, multiplied by the L square, which is 3 square, multiplied by the alpha. Here we have 1.5, sorry, that's the 1.5 alpha. That's the moment. The 1.5 is this one, and the 15 is going to be that value, the mass. So now I can solve, we can see that we only going to have the alpha to be the unknown value. I will end up with having that the total of the kinetic diagram is going to be 45 alpha, and the 45 alpha to be, sorry, the weight to be divided by the 45 to have the value for the alpha, and we can find that the alpha is going to be a negative value of 4.905 radian per second. Now done, I can substitute that in the equation 2, and I will come out that the reaction at the point A is going to be 36.8 Newton. So that's it. It wasn't that hard, but I'm going to repeat the question once again, just for confirmation. So we'll go back and see how we did the steps of the solution from this point. So let's remove that. So in the free body diagram and the kinetic diagram that we sketched earlier, the three equations we're going to have is the sigma of the forces of the x-axis is equal to the mass multiplied by the acceleration at the point G on the horizontal direction. The sigma of the forces to the y-axis on the free body diagram is equal to the mass multiplied by the acceleration at the point G to the y direction. Finally, the moment around the point A is equal to the MMI multiplied by the alpha plus the mass multiplied by the AGY multiplied by the RG/A. So if I'm going to do that directly here for this equation, the AX is unknown. It's going to be equal to the mass multiplied by the AGX. So if I'm going to go to the point G, if I would like to find the alpha at this point, sorry, the acceleration at that point is going to be equal to what we have in a rotating road. The acceleration at any point is going to have two components, going to be tangential and normal. So you can see the tangential is going to be in the y direction and the normal is going to be to the x direction. So the normal is going to be the omega squared multiplied by the r from here to here. And the tangential one is going to be the same distance multiplied by the alpha. So it's going to be alpha dot r. So now here we know we can find this one, and here is going to be found in terms of the alpha. So we can start to first to do the calculation of the accelerations. So we're going to find the normal and tangential one. Then we're going to substitute in the first equation. We can find the AX directly because it's only going to be related to the normal acceleration, which is the AGX. And here we can find a relation between the alpha and the AY. Okay, so we got that. And now we're going to try to do, well, I'm going to ignore this one. We're going to do the moment around the point A, which is going to be equal to the AG alpha, okay, the MMI of the point G multiplied by the alpha, plus the mass multiplied by the vertical acceleration multiplied by the distance from the G to the point A. Now here, this can be found, and this can be found. The mass is known, the RGA is known, and the alpha here, and here we have the acceleration of the GY, which has been found to be equal to 1.5 alpha. So we're going to put all the parameters in, we're going to solve for the alpha, and we will find that the alpha is equal to negative 4.905 radian per second, and we can substitute that in the equation 2, and we can find the AY is equal to 36.8 Newton. Okay, that's it. We're going to go to the next example very soon.